Welcome to the DIY Honda Garage channel. DTC P0139 refers to the rear secondary heated oxygen sensor, HO2S, slow response in Bank 1 of the 2011 to 2017 Honda Odyssey. This specific sensor monitors the exhaust gases after the catalytic converter to relay information about the exhaust oxygen content back to the powertrain control module, PCM. A slow response from this sensor can indicate various issues related to exhaust emissions and engine performance. The sensor is located in the exhaust system, downstream of the catalytic converter, making it crucial for monitoring the effectiveness of catalytic conversion in maintaining emission standards. If this DTC is triggered, it suggests that the sensor is not reacting within the expected time frame to changes in exhaust composition, which can impact fuel efficiency and emissions control. In the context of the Honda Odyssey, the rear secondary HO2S, which is Bank 1 sensor 2, plays a key role in measuring the levels of oxygen in the exhaust gases after they have passed through the catalytic converter. Located downstream, this sensor helps determine the overall efficiency of the catalytic converter and therefore influences fuel mixture calculations made by the PCM. If the sensor is slow to respond, the PCM cannot optimize the air-fuel mixture properly, which can lead to increased emissions and reduced fuel efficiency. The precise operation of this sensor is vital in maintaining appropriate emission levels required by law and for the correct functionality of the engine system. Thus, if a fault is detected, as indicated by DTC P0139, a thorough inspection of the more extensive exhaust system may be necessary to ensure all components are functioning as intended. The causes of DTC P0139 can vary widely, but a few primary possibilities include a faulty rear secondary HO2S that may have degraded over time or become damaged, resulting in slow response times. Exhaust leaks upstream of the sensor can also significantly affect its ability to measure accurately, as they can introduce additional air or disrupt the flow of exhaust gas. Additionally, wiring issues such as corroded connectors or frayed wires leading to the sensor can cause intermittent connections, leading to slow response readings. Each of these factors can independently or collectively cause the sensor to fail to relay accurate readings to the PCM, thus triggering the DTC. Proper diagnosis will require systematic troubleshooting to pinpoint the specific cause of the slow response. Certain symptoms may manifest if DTC P0139 is present. Most notably, the check engine light will illuminate on the dashboard, which is a standard warning signal for various engine management issues. Drivers may also notice a decrease in fuel economy, as the engine's fuel mixture may not be optimized due to the incorrect feedback from the faulty sensor. In addition, increased emissions can occur, potentially leading the vehicle to fail emissions testing, which is legally required in many jurisdictions. Furthermore, the vehicle might experience poor acceleration or unusual engine performance, making it essential for any driver noticing these signs to seek diagnostic assistance promptly. Recognizing these symptoms early can help mitigate more severe engine damage or compliance issues down the road. For the first troubleshooting step regarding DTC P0139, begin by turning the ignition switch to the on position, which provides power to the vehicle's electrical systems without starting the engine. This step is crucial as it allows technicians to access essential diagnostic data while ensuring proper preparations for the troubleshooting process. In this stage, it is imperative to record all freeze frame data available in the vehicle's onboard diagnostic system. Freeze frame data provides a snapshot of the vehicle's operating conditions at the time the fault was detected, which can be invaluable for diagnosing the cause of the problem. Additionally, reviewing any general troubleshooting information specific to the DTC is beneficial, since it can provide insights into frequent causes or effective methods for resolution. Collecting this data effectively sets the foundation for the remaining troubleshooting procedure. The next step involves clearing the DTC using the Honda Diagnostic System, HDS. The HDS is a sophisticated tool designed specifically for Honda vehicles, allowing technicians to interface with the onboard computer systems efficiently. Clearing the DTC is crucial before performing any further diagnostics, as it resets the error codes stored in the PCM and allows the technician to determine if the issue is persistent or if it was an intermittent fault. By removing the codes from the system, subsequent tests can provide clearer information on the current state of the rear secondary HO2S and its functionality. The technician should be prepared for testing by ensuring that the engine conditions specified in the following steps can be achieved safely and accurately after completing this process. In this step, the technician should start the engine and carefully hold the engine speed at 3,000 RPM without load, such as when the transmission is in park or neutral. Keeping the engine at this elevated RPM simulates conditions that generate optimal exhaust flow, while allowing the sensors to reach stable operational parameters quickly. This step is essential because it allows the oxygen sensor to respond appropriately, helping to diagnose its performance. The technician needs to monitor the engine until the radiator fan activates, an indication that the engine has reached a certain temperature threshold. Once the fan engages, the technician can allow the engine to idle, creating the right conditions for observing how the HO2S operates when in a more stabilized state. The continued monitoring of changes in readings at this stage is vital for accurate diagnostics. During this step, the technician must conduct a test drive under specific conditions to facilitate proper evaluation of the vehicle's performance. The engine coolant temperature, denoted as ECT, should be above 158 degrees Fahrenheit, 70 degrees Celsius, to ensure that the engine and its components are within operational ranges that allow for accurate sensor testing. During this test drive, the technician should keep the vehicle in drive and maintain a steady speed between 55 to 75 miles per hour, 90 to 120 kilometers per hour, for approximately 1 minute. Following this period, the technician should decelerate with the throttle fully closed for 10 seconds. This approach ensures that the pressure dynamics in the exhaust system change, allowing the rear secondary HO2S to react to the variations effectively. Accurately following these drive conditions is critical for gaining insights into whether the sensor is behaving appropriately under normal operational conditions. After completing the test drive, monitoring the onboard diagnostic OBD status for DTC P0139 and/or DTC P0159 using the HDS is the next crucial step. The HDS will provide diagnostic results indicating whether the vehicle remains in a failed state regarding these DTC codes. If the system indicates a failure, further investigation is warranted to determine the root cause of the issue. Conversely, if the HDS indicates passed, it suggests that, at this moment, the system is functioning correctly. However, intermittent problems may still exist, so examining connections and terminals related to the secondary HO2S and the PCM is advisable. If the system is still in an executing state, keeping the vehicle on the road until a definitive result is shown may be necessary. Should the HDS return an out-of-condition reading, this requires the technician to revisit Step 3 and recheck the initial conditions surrounding the sensor operation. For this step, it is essential to turn the ignition switch to the lock position, 0. This action allows the vehicle's systems to fully shut down, which is necessary before performing any repairs or replacements to avoid electronic malfunctions. Once in the lock position, the technician should prepare to conduct further actions based on the results observed in the previous steps. This typically involves planning out the method for either replacing the secondary HO2S or checking the wiring and connections for faults. Ensuring the ignition is off during this phase is crucial for both safety and the integrity of diagnostic systems. Thus, taking a systematic approach at this juncture will ensure the next steps are executed properly, reducing the risk of overlooking further related issues. In this step, replacing the secondary HO2S, specifically the one designated as Bank 1 Sensor 2, is crucial if prior diagnostics indicated an issue. The replacement of this sensor is essential to restore optimal engine performance and emission standards compliance. This sensor is typically located in the exhaust system post-catalytic converter, so technicians should follow manufacturer guidelines for proper access and removal. When undertaking this replacement, care must be taken to avoid damaging surrounding components and wiring. Once the new sensor is installed, it's advisable to ensure that all connectors are securely attached and are free from corrosion. A successful replacement can significantly affect the vehicle's overall efficiency and emissions capabilities. Once the replacement of the secondary HO2S is complete, turn the ignition switch to the on position 2 to prepare for resetting the powertrain control module PCM. This step is necessary to allow the vehicle's computer systems to recognize the new sensor and recalibrate as needed. By supplying power to the electrical components, the technician enables communication with the HDS for further diagnostic procedures. Ensuring that the ignition is in the correct position also minimizes the risk of unintended startup while working on the electronic systems. Proper execution of this step is vital, as it directly contributes to the efficacy of the subsequent PCM reset, which aims to clear any remnants of previous error codes and prepares the vehicle for effective functionality post-repair. After activating the ignition to the on position, using the HDS to reset the PCM becomes the next substantial step. The PCM contains crucial learning algorithms and information that dictate how the vehicle operates, and resetting it removes any previously stored codes, including DTC P0139. This process is essential to ensure that the new secondary HO2S is integrated into the vehicle systems properly. Once the old codes have been cleared, it enables the vehicle systems to adapt to the new sensor's readings. This reset will pave the way for more accurate diagnostics in the future and improve the vehicle's overall fuel management and emissions control. Completing this step ensures that the PCM is aligned with the current state of the vehicle following the replacement. Following the PCM reset, the next step involves performing the PCM idle learn procedure. The idle learn procedure is a systematic process where the PCM recalibrates its understanding of idle RPM and characteristics with respect to the new sensor data. It is crucial to allow the engine to idle without any load until the radiator fan engages, as this indicates the engine is at the proper operating temperature. This procedure promotes optimal engine performance and ensures the PCM can accurately control fuel delivery and air mixture. Completing this step effectively allows the engine to reach a normalized state, facilitating smoother operation and improvements in both fuel efficiency and emissions levels. A successful idle learn procedure may significantly enhance the vehicle's drivability and responsiveness. In this step, the technician should allow the engine to idle without load in the park or neutral position until the radiator fan engages. This condition signifies that the engine is operating at optimal temperatures and conditions for the HO2S to respond effectively. This is a crucial continuation of the prior idle learn procedure, and attention should be given to any abnormal noises or behaviors that may indicate underlying issues not yet addressed. Staying observant during this phase can provide insights into the overall health of the engine, as various components, including the cooling system and exhaust, will actively integrate information during the idle period. Properly monitoring the engine during this time helps ensure that all systems are functioning correctly before conducting subsequent drives to evaluate sensor performance. This reinforces the importance of thorough diagnostic evaluation in the troubleshooting process. For Step 12, the technician will test drive the vehicle again under the previously specified conditions. It is essential that the engine coolant temperature remains above 158 degrees Fahrenheit, 70 degrees Celsius, throughout the test period to ensure the systems are functioning under operational norms. The vehicle should be driven in drive at a steady speed of 55 to 75 miles per hour, 90 to 120 kilometers per hour for approximately 1 minute, before decelerating with the throttle fully closed for a duration of 10 seconds. This controlled driving scenario allows for accurate monitoring of the secondary HO2S's performance in response to varying exhaust conditions, vital for making informed diagnostics. Ideally, this period should yield valuable data regarding the sensor's response time and capability to relay accurate readings. Performing this drive test effectively verifies if the issues related to DTC P0139 persist, allowing further adjustments or checks to be made as part of the comprehensive troubleshooting process. After completing the second test drive, check for pending or confirmed DTCs using the HDS, focusing on DTC P0139 and DTC P0159 if applicable. This assessment is crucial to verify whether the replacement of the secondary HO2S had a positive effect in resolving any ongoing issues. If the same DTCs are still indicated, it may imply persistent problems, potentially stemming from poor connections or loose terminals at the secondary HO2S and the PCM. The technician should take this opportunity to closely inspect the integrity of the wiring and associated connectors, as these components are integral to ensuring accurate sensor readings. If issues are found, further corrective measures will be necessary. In contrast, if no DTCs appear, the system may have resolved the problem, and the technician can determine the next steps based on the absence of error codes. This leads to a more systematic approach to resolving vehicular sensor issues effectively. The final step in the troubleshooting process involves monitoring the OBD status for DTC P0139 and/or P0159 using the HDS once more. This crucial step checks to determine whether the HDS indicates a passed status, indicating that all systems are functioning correctly. This confirmation ensures that all repairs were made effectively and that no lingering issues remain related to the secondary HO2S sensor's performance. If the HDS indicates passed, the technician can conclude the investigation and documentation process. On the contrary, if the system shows any error status or suboptimal readings, it will necessitate further investigation into the sensor, connections, or other supporting components. Safeguarding these checks is imperative to moving forward confidently, ensuring that the issue is wholly resolved, thus adding reliability to the vehicle's overall operations. After successfully following through with the troubleshooting and repair processes, it is essential to perform a final verification to confirm that the system is fully functional. This involves ensuring that the secondary HO2S operates correctly within specified parameters and that no new or lingering DTCs have appeared. Test driving the vehicle again under controlled conditions will confirm if the system operates as expected, providing assurance that previous issues have been effectively addressed. Failure to conduct such verification could lead to overlooking underlying problems that may yet affect performance or compliance with emissions regulations. Ultimately, this thorough verification process helps maintain the vehicle's reliability and efficiency while preventing potential future issues. Preventive maintenance for the oxygen sensors, particularly the secondary HO2S in the Honda Odyssey, involves ensuring routine inspections and maintenance of all related components. Regular checks for sensor performance and verifying that the exhaust system is free from leaks are critical to maintaining optimal fuel economy and emissions. Additionally, inspecting wiring connections and ensuring that all terminals are secure can prevent potential issues from arising in the future. This proactive approach not only saves on costly repairs, but also enhances the longevity of the vehicle's engine systems. Regular maintenance intervals can significantly reduce the risk of sensor-related failures, ensuring that the vehicle remains compliant with emission standards effectively over time. To conclude, understanding the DTC P0139 and its implications is essential for maintaining the health and efficiency of the 2011 to 2017 Honda Odyssey. The troubleshooting process, a meticulous journey from diagnostic verification through repair and verification, underscores the importance of accurate diagnostics in resolving persistent issues effectively. Furthermore, this guide highlights that proactive maintenance, which includes routine checks and preventive measures, is pivotal in mitigating future problems concerning oxygen sensors and exhaust systems. Recognizing early symptoms, following the diligent troubleshooting steps, and ensuring proper maintenance enrich vehicle performance and longevity. Thus, following this structured approach can ensure that the vehicle operates optimally while remaining compliant with environmental standards. Please like and subscribe to the channel. See you next time.